Okay, now the second part of this chapter is we're going to learn how to linearize nonlinear relationship. Linear regression is actually a great way or a great technique to fit baseline to data in which the relationship between the independent and the dependent variables is linear. But in real situation, in real life, this is not always the case. Okay, so sometimes we encounter situation where the relationship between the dependent and the independent variables are not linear. So let's look at this figure here. So obviously we can see that this has no linear relationship at all between the variables. And uh, if we fit a linear line for this data, it will definitely not represent the system at all. So how are we going to tackle this problem? This is why we are learning this topic today. So basically, transformations can be used to express the data in a form which is compatible with linear regression. So we are going to look into three types of model here. The first nonlinear model is what we call as exponential model. The second one is power model, and the third one is saturation growth rate model. So these three models are the most commonly used models in engineering, specifically chemical engineering. You will encounter many types of these models throughout your 4 years program. So as you can see, there are three linear relationship here. So these are the linearized versions of corresponding models from simple transformation. So this one is from the exponential model after linearization, and this is for the power model, and this is for the saturation growth rate model after simple linearization. So after transformation, you can see that the x-axis for the exponential model stays the same, but for the y-axis, it has been transformed from y into ln y. And the slope is b1 and the intercept is ln a1. For the power model, both x and y-axis have been transformed into log x and the log y-axis with a slope of b2 and intercept log a2. And for the saturation growth rate model, both the x and y-axis are transformed into 1 over x and 1 over y with the slope b3 over a3 and intercept log 1 over a3. So we will see each model after this one by one, how actually we transfer this into this, the linearized version. Okay, so let's look at the first model, what we call as exponential equation. So this is the general formula for the exponential equation. Y equals to a1 e b1 x. All right, so by taking the natural log for both sides, we reach to ln y equals to ln a1 plus b1 x. We bring here ln e, and as you know, ln e will equal to 1. So this leaves us with ln y equals to ln a1 plus b1x. So if you look at this linear version, so this is x and this is your y. So it's actually your x-axis and your y-axis, and b1 is the slope and ln a1 is the intercept. So a plot of ln y versus x will yield a straight line with slope of b1 and intercept of ln a1. So for example, fit an exponential model to this data here. Okay, meaning we need to come up with the best fit or the regression line for this exponential model. So what you can do is you table out your data. This is your X column. This is the column for the Y data. And since this is an exponential model, the y-axis, you need to transform it into ln y. So create another column here as ln y and just calculate for each of the data. This is actually ln 750 and this is actually ln 1000 and 7.244228 is actually ln 1400 and so on and so on. So you need to also to calculate the summation, right, for each of your axes. So x-axis stays the same and y-axis need to be transformed into ln y, and you also need x squared in order for you to calculate your slope. So x squared is just simply the first one 0.4 squared, this one 0.8 squared, and so on and so on. And you also need the summation. And another one is the multiplication of your two axes. So here meaning xi times ln yi. So the first part here is 0.4 times 6.620073, you get this. And so on and so on and so on. And you have this total for the xi times ln yi. So here I'm listing down all the items that we need in order to calculate the slope and the intercept. So you need your n. N is the number of data. We have 6. And then you need summation of x, summation of x squared, summation of ln y. This is the y-axis. And the summation of x times ln y. Once you have all these elements, and also you need your mean, arithmetic mean for the x and the arithmetic mean for your ln y. Once you have all these elements, then you can substitute into the equation of the slope. So this is the equation of the slope. Okay, just substitute all the elements and all the values into the equation. So you will get your slope as 0.843. Once you got your slope, you can substitute into the equation, which equals to the mean of the y minus b, the slope, and the mean of the x. So just substitute everything. You got your ln a equals to 6.25. Okay, so let's put everything, the slope and the intercept, into the regression straight line. So this is the straight line formula for the the straight line best fit formula for the exponential model. Ln y equals to ln a plus bx. So ln y equals to ln a is simply 6.25 plus b is the slope 0.843 times x. So you got your best fit for the exponential model. So this is your final answer. But let's say you need to also represent your final answer into the exponential form, okay, not the linear form. So you need to transform back into the exponential version. So in the nonlinear exponential model, the equation is y equals a times exponential bx. Okay, how do you calculate your a? It's just simply ln a here equals to 6.25. So you can work out what is your a. A equals to exponential 6.25 equals to 518. So this is your a. And b stays the same. You don't need to transform anything, 0.843. So just substitute everything into the exponential equation. So y equals to a e bx equals to a 518 exponential b 0.843 times x. So you have finally reached to the end of the solution, in which you can come up with the regression line and also with the exponential formula for the x and y data provided. Okay.